So A, B, C, D are structural isomers with a molecular formula C4H10O. So the first thing is to identify what could be C4H10O. So there is one oxygen. So this cannot be a carboxylic acid. So because carboxylic acid has two oxygen, cannot be an ester. Then this cannot be an amide because there is no nitrogen. So this could be three things. One is alcohol. So this could be, so I will try to do this in the board. Okay. So which is very, very easy for you guys to understand. So we have A, B, C, D given. So C4H10O. So this could be an alcohol, can be an aldehyde, can be ketone maybe, and can be an ether maybe, because all these contain single oxygen atom. Okay, so we will move on. So we have this formula. All four isomers reacted with metallic sodium to evolve H2 gas. So from this point, you have to understand normally alcohols with OH react with sodium to give ONA plus hydrogen. So I'll cut these things because ether is inactive and aldehyde and ketone does not normally react with sodium like this. So we have come to a conclusion. This is alcohol. So C4H10O is alcohol. Then we will move on further. Of the four isomers, only A exhibited optical isomerisms. Okay, so A is optical. And B, C, and D were added separately to conjugate Cl containing Cl2, which is our Lucas reagent in this case. B became very rapid, so B is a tertiary alcohol because it is very rapid. And CD was very slow, so basically these two could be primary alcohols. Yeah. When C and D were heated with conc H2SO4, E and F were respectively obtained. So when you have C and D, you add conc H2SO4, you get E and F, right? E and F are structural isomers with the molecular formula C4H10H8. So this, you know, this should be an alkene now. Neither E or F exhibit geometric isomerism. So no geometry, no cis or trans. When E and F were treated with HBr, G and H were respectively obtained. So you treat this with HBr and G and H is obtained. So they are telling G is showing optical isomerism. Right. So we have to predict the structures now. Right. So we have all piece of information that is necessary. Now we have to predict. Now A is optical, which means I can try to draw A. Is optical, so there should be a carbon with different groups. Okay, and one more thing that I have to check here. Yeah, so they have given only A shows optical isomerism. So how do you use these 4 carbon atoms to determine the optical activity of A? So there should be 4 different groups. So 2 carbons, 3 carbons, 4 carbons. If I add these 4 carbons like this, it's a problem because this does not become an optical active compound. So there should be a way that I can add these compounds in order to get optical activity. So if I put 1 hydrogen here and 2 carbons here, for an example, so I can put OH here and I can make this as CH3 and this as CH2, CH3. So I see a chiral center where there are 4 different groups and 1, 2, 3, 4 carbons, hydrogen 3, 2, 5, 3, 8, 9, 10, and 1 oxygen, which matches my chemical formula that is given. Okay, so A could be this one. And you try to see any other combination of using this chemical formula C4H10NO, will end up with this one. There is no other way. So this is the idea of this compound, because all evolve H2 with sodium, so which gives the idea this also should be an alcohol. And B is a tertiary alcohol, so eventually you need to understand, so there should be like this. Since this is a tertiary alcohol, so this is a tertiary alcohol, so this is B, this is A. Then we go to our important part. So determining A and B is straightforward, they are not hard. Now we go to C and D. So C and D is very slow, which gives you the idea this should be a primary alcohol. So we try to manipulate this and get a primary alcohol using this one. So what is the easiest, simplest way of getting a primary alcohol using this 4 carbon atom? That is the linear chain. So we can write down like a linear chain: CH3, CH2, 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 OH. So this is a linear chain. Okay, so this is the simplest form of a primary alcohol. Then I need to change this chain form in order to get another primary alcohol. The simplest possible way to change here, since this has more than 1 additional carbons here, what I can do is I can make a branch structure. Instead of joining here, I can join this here. So which gives me the idea, this is CH2OH, and I'm going to attach through this carbon, and these two will be then the terminal. It's like this. So there is CH here, and there is CH3, and there is CH3. So still I am going to end up with a primary alcohol. What I did, instead of attaching here, I am going to attach here. That's all. Then this 2 becomes CH3, which is this. And this is going to be CH, that is attached to CH2OH. Okay. So still I find 1, 2, 3, 4 carbons and 6, 7, 8, 9, 10 hydrogen and 1 oxygen. So same compound. So one of these two is going to be my C and D. Then they say they treat this with conc H2SO4. So we will draw this again and come to this reaction scheme again. So I think this is CH3, CH2, CH2, CH2OH, and this is CH3, CH, CH3, CH2OH. We don't know yet whether this is C or this is D, because you can identify this here at this point, because D shows optical activity which is from E and E is from C. Okay, so we treat this with conc H2SO4. So we try to treat this with conc H2SO4. So we will get this one CH3 CH2 and CH double bond CH2. This is one. And then when we treat this one with conc H2SO4, we will end up with CH3 double bond CH2 and CH3. And then when you add HBr, so when you add HBr, this will become CH3, CH2, and there will be Br here, and there will be CH3 here. And when you add HBr here, this will be CH3, and Br here, CH3, and CH3. So now I see here, there is a chiral center here, because 4 different groups, but here all 3 CH3 groups are same. Okay, you see here 4 different groups: Br, hydrogen, CH3, CH2, CH3. So it gives me the idea now. G is this one, right? This is G, and the compound with 3 different CH3 groups. Now it should be H, because out of G and H, only G exhibits optical isomerism. So G is derived from E, so this should be E then. This should be F then. So if this is E and F, so automatically this is C here and this is D here. Okay. So this is the scheme for our particular reaction. So if you know your alcohol chemistry very well, so you can automatically and easily find an answer for this particular question. It's not that hard, right? So first one is very easy, B is very easy. So C and D you cannot determine straightforward by using 2 different structures. The only thing is you have to move forward using the reaction with conc H2SO4 and then adding HBr, and then you try to see whether what is G and what is H. Then based on G and H, you need to find what is E and F, then what is C and D. Have to go back from the final step. Right, I will share the screen now. So you need to draw all these A, B, C, D, E, F, and G and H in these boxes. Okay. When A and C were reacted with PCC, I and J were respectively obtained. Draw the structures of I and J in the boxes given below. PCC is pyridinium chlorochromate. So you know it's a mild oxidizing agent. So what is A here? So we know that A is there was a chiral center like this. So one of these should be OH, and there was hydrogen, and there was CH2, CH3. So when you use PCC for A, you can see there is an oxidization that is happening, oxidizing. So basically this could become a ketone. So there will be CH3. The carbonyl carbon is OH is converted to a carbonyl carbon. So there will be CO here. And this could become CH2 and CH3. So this is a ketone, right? So very nice. And what is C here? So C is our compound that we discussed here. C is primary alcohol. So when you do PCC, you will get an aldehyde. So CH3, C here, C is A here. So CH3 CH2, then another CH2, another CH2, and this is OH. Okay, this is C. So you add PCC, pyridinium chlorochromate, which is a mild oxidizing agent, and your CH2OH is going to end up in the aldehyde form. Okay, so you can imagine this is a ketone, this is an aldehyde that is going to form. There is the rest of the compound here. So this is done. Then how do you identify this ketone and aldehyde? You can do the tolerance test. So they have not asked here, but if they have asked, you can mention that. Okay. Right. So moving on. So we have given a set of questions as a general scheme. So you have to predict the products. So HBr peroxide gives the anti-Markovnikov product. So which is here you will obtain a Br, and here you will add the H, and this will become a single bond because this is anti-Markovnikov in the medium peroxide. So this is benzaldehyde. So you add 2,4-DNP and dehydration. So you know what is going to happen here when you have benzaldehyde, which is CHO. So you know aldehydes, they are reacting with 2,4-DNP. Then there will be this bond with carbon and DNP. Diazonium salt with this is called beta-naphthol. Naphthol means when you have two benzene rings without OH, we normally say that as naphthalene. Okay, when you have two benzene rings without OH, we say that as naphthalene. So when you have OH here, we say naphthol. So this is actually beta-naphthol, and there will be this N2 bond here at this ortho position actually. Okay, this is the activated process, and there will be this bond that with N2 and the benzene ring. In fact, this will be like this. So there is OH here. So here the bond will be like this. Okay, it's the benzene ring N2. And SI chloride with ammonia, it will form the ammonia amide CONH2. Then you will have here the benzoic acid here with conc HNO3 conc H2SO4. So COOH is a meta director, so there will be NO2 in the meta position. And this is Clemmensen reduction. CO will be converted to CH2, and here CH3CHO with the silver diamine complex. So this will be converted to a carboxylic acid because this is the oxidization. So CH3 oxidation, in fact, sorry. CH3COOH. And this is going to reduce, forming the silver mirror. Ag plus, Ag0. And here's NaNH2. So there will be CH3 carbon, triple bond, another carbon, Na. So there will be Na plus, C3 minus. Okay. But don't forget, if don't write like this, okay? CNA plus minus. Do you get my point? This is CH3. This is correct, but this is wrong. Right? This is wrong, right? Because there is no bond between C minus and Na plus. This is just an electrostatic attraction. When you remove this hydrogen, there is only electrostatic attraction. Right? So other than this, when you add these two, there will be ammonia that is forming. But you don't need to write ammonia here because they are only asking about the major organic products. Okay. And H2PD, you will convert this into a alkane, and alcohol with Br2, there will be the white precipitate that form at the ortho and para positions, forming the white precipitate at bromine is tri-substituted. Okay, so these reactions are very straightforward, very common theory, in fact. And finally, there is part C, write the mechanism for the reaction between CH2, C2H5, CHCl, C2H5, Br2, CCl. So I think I don't have to discuss this because this is very simple. You will have the double bond and you will have the Br thing here. So this is going to attack this and this is going to form here. And there will be this negatively charged which attack this carbon after the carbocation formation. So the important step that you should show here is the cyclic carbonium. In fact, if you have a carbocation like this is a carbocation. But here when you draw the structure and see, you can show this one. Here I will draw this one. So you have to show this cyclic bromonium, okay? This is an important step of this mechanism, cyclic bromonium. You have to show this in the mechanism. If you did not show this one and you write down all the other steps, so in the evaluation they have given us, so don't give marks if you have not indicated the cyclic bromonium. This is very important to understand, right? Okay, so this summarizes our discussion of the structured assay. So